Pick up a magnet, one of the small silver discs off the door of a fridge, 5 grams at most, and hold it a centimeter above a steel paperclip. The clip jumps. It hangs there in the air, and underneath it, pulling the other way, is the entire planet. 5,900 million kilograms of rock and iron and ocean, every mountain range and every continental plate, all of it losing instantly to something you could hold between 2 fingers. That contest is settled by a factor of 10 to the 36th power, a 1 with 36 zeros behind it. And here is the part nobody mentions while you are playing with the magnet. Nothing in physics explains that number. It was measured, written down, and inserted into the equations by hand, along with the 3 others like it. There are exactly 4 fundamental forces in the universe, and by the end of tonight, you will know precisely why nobody can say why. Before we begin, if sitting with a question this large is how you like to fall asleep, a like or subscribe would mean a great deal. It is a small thing for you, and it keeps this channel going. Now, let's ease in. Everything that has ever happened to you was one of 4 things. That is not a simplification made for the sake of a comfortable evening. It is the actual, current, working inventory of physics. Every push and every pull, every collision, every chemical reaction inside every cell you are made of, every photon that has ever landed on your retina, every atom that has ever held together long enough to be part of something, every star that has ever burned, and every one that has ever stopped, all of it, without exception, has been produced by 4 fundamental interactions. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. 4 entries. That is the whole list. The word fundamental is doing careful work there. It does not mean important, and it does not mean powerful. It means that nobody has ever succeeded in showing that these 4 are built out of anything simpler. Friction is not on the list, because friction is electromagnetism between the surface layers of 2 objects. Pressure is not on the list, because pressure is electromagnetism again, plus a rule about how identical particles are allowed to share space. The tension in a rope, the sound of a door closing, the taste of something sweet, the way your muscles contract when you turn over in bed, all of it is one force, wearing a different costume for each occasion. Chemistry, in its entirety, is a single fundamental interaction operating in a single narrow regime. Biology is chemistry with more steps. You could spend an entire lifetime cataloguing the ways matter behaves, and every single item in your catalogue would resolve into one of 4 things. 2 of those 4 you have never felt and never will. The strong nuclear force reaches about 1/4 of a meter before it stops, roughly the width of a single proton. The weak nuclear force reaches about 1,000 times less than that. Neither of them extends beyond the interior of an atomic nucleus. You have no sense organ that could ever register them, no experience that has ever included them directly, and yet without the strong force there would be no atom heavier than hydrogen anywhere in the universe, because nothing would hold 2 protons together against their own electrical repulsion. Without the weak force, the sun would not shine, because the first step in turning hydrogen into helium requires 1 proton to change into a neutron, and only the weak force can do that. 2 forces you cannot perceive are responsible for the existence of every element in your body, and for the fact that there is a star close enough to keep you warm. The other 2 you know intimately, though only one of them announces itself. Electromagnetism you experience constantly without noticing, because it is doing everything. It is the reason the mattress underneath you pushes back instead of letting you sink through the floor. The reason light reaches your eyes. The reason your body holds its shape. And gravity you notice, because gravity is the one that makes you tired. It is the reason lying down feels like relief. Here is the first thing worth sitting with. That list of 4 has not changed in about 90 years. Physics has spent the intervening decades building instruments of absurd sensitivity, specifically looking for a fifth entry. Torsion balances so delicate they can register the gravitational pull of a hand-sized weight from a meter away. Satellites in free fall testing whether two different materials drop at exactly the same rate, to a precision of 1 part in 1,000 million. Particle colliders that reach energies 1,000,000 times higher than anything in the nuclear reactions that power the sun. Underground detectors watching for interactions so rare that a signal of one event per year would be a triumph. Every one of these experiments could, in principle, have turned up something that does not fit on the list. None of them has. There is no confirmed fifth force. There is not even a broadly accepted candidate. So the list is 4, and it appears to be complete, and it has appeared to be complete for a very long time. Now, 4 is not a natural number for a universe to choose. That sentence is going to come back several times tonight, and I want to plant it now, while it still sounds like an idle remark. Think about how the list has behaved historically. It has always been in the business of getting shorter. Before Newton, the physics of falling apples and the physics of orbiting moons were two separate subjects with two separate sets of rules, and Newton showed they were one thing. Before Maxwell, electricity and magnetism were two subjects, with separate textbooks, separate laboratories, and separate practitioners, and Maxwell showed they were one thing. In the 1960s and 70s, electromagnetism and the weak force were shown to be two faces of a single interaction. Every time somebody has looked hard at two entries on this list, the two entries have collapsed into one. The list has never once grown. It has only ever shrunk. And it stopped shrinking about 50 years ago, at 4. If you had been watching that process from the outside, watching a number go from many to several to 4, you would have made an obvious prediction. You would have said, give them another few decades, and it will be 1. That was, in fact, the near-universal expectation of physicists in the 1970s. The mood in the field was that the end game had begun. The tools were working. The pattern was clear. The next unification was expected within a generation, and there were serious people who thought they might see the whole thing finished in their lifetimes. It did not happen. It has not happened. And the reasons it has not happened are far more interesting than a simple story about a hard problem taking a long time. Because here is what makes this a mystery rather than a delay. 3 of these 4 forces are not merely similar. They are built, mathematically, out of exactly the same idea, one single principle, which I will show you in detail a little later, that generates each of them automatically when you feed it a different starting ingredient. 3 instances of one construction. They look, from a distance, like 3 settings on the same machine, and they refuse to merge. The 4th is not built out of that idea at all. Gravity comes from somewhere else entirely, describes something else entirely, and when you try to write it in the same language as the other 3, the mathematics does not merely become difficult. It breaks in a way that has now been understood in precise technical detail for 40 years and repaired by nobody. And then there are the numbers, because the 4 forces are not 4 comparable things with slightly different settings. Their strengths are so wildly different from one another that the comparison stops feeling like physics and starts feeling like a mistake in the arithmetic. That is where we are going next, and I would like you to hold on to something before we do. Every one of those 4 strengths is a number that had to be measured, not derived, not predicted, not calculated from any deeper principle. Somebody went into a laboratory, made a measurement, and wrote the result down, and that number went into the theory by hand. The standard model of particle physics, the most accurately tested scientific theory ever constructed, capable of predicting some quantities to 12 decimal places, contains around 19 of these hand-inserted numbers, and it cannot explain a single one of them. It tells you, with extraordinary precision, what the universe does. It has nothing at all to say about why the universe was set up that way. So the inventory is complete, and the inventory is unexplained. There are 4 fundamental forces. Nobody knows why there are 4, rather than 3, or 7, or 1. Nobody knows why they are these particular 4, and nobody knows why their strengths are what they are. Tonight we are going to walk all the way through that problem, slowly, one piece at a time. We will look at what each of the 4 actually is, and then at what a force even means in modern physics, which turns out to be something considerably stranger than a push or a pull. We will follow the 2 great unifications that worked, in enough detail to see why everyone was so confident the third would follow. Then we will follow the third one down into a mine in Japan, where 50,000 tons of water have been watching for something that has not arrived in 40 years. But before any of that, we need to look at the numbers. Not what the forces do, how strong they are, relative to one another. Because the first crack in this whole picture is not subtle, and it is not hidden in an equation. It is a single ratio, and it is so large that there is almost nothing in human experience to compare it to. Take 2 protons and hold them a small distance apart. They will do 2 things at once. They will repel each other electrically because both carry positive charge, and they will attract each other gravitationally because both have mass. 2 of our 4 forces acting on the same pair of objects at the same moment over the same distance. This is about as clean a comparison as physics ever gets to make, because every complication cancels out. Same particles, same separation, same instant. All you are measuring is the relative strength of the 2 interactions themselves. The electrical repulsion wins. It wins by a factor of about 10 to the 36th power. That is a 1 followed by 36 zeros. Written out in full, it is a million, 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 million. 6 millions strung together. And I want to be clear that this is not a figure of speech or a rhetorical flourish. It is a ratio of 2 measured coupling constants. Electromagnetism's strength, expressed in the standard dimensionless way, is the fine structure constant, 1 over 137.035999177, a number we now know to about 1 part in 6,000 million. Gravity's strength between 2 protons, expressed in exactly the same way, is about 5.9 times 10 to the minus 39. Divide one by the other, and you get 10 to the 36th. Same units, same method, same protons. Let me put a body on that number, because exponents slide off the mind. Imagine you are lying in bed, and on the table beside you there is a small magnet, one of the little silver discs, no bigger than a coin, 5 grams at most. Underneath it, on the wood, is a steel paperclip. You lift the magnet, hold it a centimeter or 2 above the clip, and wait. The clip jumps. There is a faint tick as it strikes the underside of the magnet and holds there, and now it is hanging in the air with nothing beneath it. Consider what just lost that contest. Beneath the paperclip is the entire planet. 5.97 times 10 to the 24th kilograms of iron and rock and ocean, every mountain range, every continental plate, the whole molten core, all of it pulling downward on that clip with the full gravitational authority of a world. And it was defeated, instantly and without effort, by a piece of metal you could swallow. Not by a machine, not by a magnet the size of a car, by a 5-gram disc, using a fraction of its field, on one small steel object. The Earth had every advantage. It had all the mass, and it was not close. That is what a factor of 10 to the 36 means in the room you are lying in. Every time you pick up a spoon, every time a leaf holds itself onto a branch in wind, every time your own skeleton declines to fold under your weight, the same contest is being settled the same way. Electromagnetism holds the shape of everything. Gravity is a background hum. Now widen it out to all 4. Set the strong nuclear force to 1. Call it the unit, since it is the strongest thing we know. On that scale, electromagnetism comes in at roughly 1 over 137, so let us say a bit under 1%. Already a factor of 100 down from the leader. The weak nuclear force, at the energies of everyday matter, lands somewhere around 1/1,000,000th. Another 4 orders of magnitude down, and gravity comes in at about 10 to the minus 38. Look at the shape of that list. 1, 100th, 1/1,000,000th, and then a drop of 32 more orders of magnitude to reach the 4th. There is no pattern. They are not spaced evenly. They are not powers of a common base. They are not related by any factor that appears anywhere else in physics. 3 of them are within a few orders of magnitude of one another, huddled together, and then there is an enormous empty gulf, and gravity is on the far side of it, alone. And every one of those numbers had to be measured. None of them is derived. Nothing in any accepted theory says the strong force should be about 100 times electromagnetism, or that gravity should be 38 orders down. Those values were found by experiment and inserted into the equations by hand, and if you changed them in the equations, the mathematics would not object. It would simply describe a different universe. There is a detail here that I find quietly damning. Of the 4 coupling strengths, the one we know least accurately is gravity's. Newton's constant, big G, is known to a relative precision of about 2 parts in 100,000. That sounds respectable until you compare it with the fine structure constant, which is known to about 1 part in 6,000 million. We understand the strength of electromagnetism roughly 100,000 times more precisely than we understand the strength of gravity. And the reason is exactly the thing we have been discussing. Gravity is so weak that measuring it requires isolating an experiment from every electrical, magnetic, thermal, and seismic disturbance on a noisy planet. Different laboratories, using torsion balances of exquisite care, have produced values for big G that disagree with each other by considerably more than their stated uncertainties, and have been doing so for decades. The oldest force in physics, the first one ever written down mathematically, is the one whose strength we have the most trouble pinning down. So why does gravity run the universe? Because it never cancels. That is the entire answer, and it is worth understanding properly, because it is also one of the strangest asymmetries in the whole picture. Electric charge comes in 2 kinds. Put enough positive and negative together, and they neutralize each other so completely that a rock, a planet, a star, a galaxy is electrically invisible at a distance, despite being made of particles that individually carry the second strongest force in existence. Color charge, the strong forces version, comes in 3 kinds and cancels even more aggressively. It will not even let its carriers out of the room. The weak force cannot reach past a nucleus. Mass and energy come in 1 sign only. There is no negative mass. Nothing cancels gravity, nothing screens it, nothing shields it. You cannot build a gravitational Faraday cage. So gravity just accumulates. Add more matter and you get more gravity, always, with no opposing contribution, forever. The weakest of the 4 forces by a factor of 1,000 million is the one that assembles planets, ignites stars, holds galaxies in shape, and determines the large-scale structure of everything there is, not because it is strong, but because it is the only one that never turns off. And now, the part I would like to leave you with before we move on. Of these 4 forces, there is exactly one you have ever consciously felt. Not deduced, not measured, not read about. Felt. It is not electromagnetism, even though electromagnetism is what physically stops your hand when it meets a table. Your nervous system reports that as touch, not as a force. It is not the strong force, which built every atom in you, and which you will never sense. It is not the weak force, which lit the sun, and which you will never sense either. It is gravity. Gravity is the ache in your legs at the end of a long day. It is why carrying something heavy up a staircase is hard, why falling is frightening, Why the body of an astronaut begins to change within days of losing it. It is the reason lying down is a relief, and the reason getting up in the morning takes an act of will. Almost every physical sensation of effort you have ever had in your life has been a negotiation with gravity. And gravity is the one physics can barely fit into its own mathematics. The force that has shaped every hour of your embodied experience is the outlier, the one 38 orders of magnitude off the pace, the one that will not go into the equations with the others, the one whose strength we cannot even measure properly. The force you know best is the one we understand least. That is the first crack, and it is a wide one. But a difference in strength, on its own, is not necessarily a mystery. Things can just be different sizes. The reason this ratio is a genuine problem, the reason physicists lose sleep over it rather than shrugging, only becomes clear when you understand what a force actually is in modern physics. And it is not a push. It is not a pull. It is not anything you have been shown in a diagram with arrows on it. It is a bookkeeping fee. The picture most of us carry of a force is a diagram with an arrow on it, an object, a direction, a magnitude. Something pushes, something else moves. That picture is not wrong, exactly, in the way a map of a city is not wrong. It is just several levels of abstraction above what is actually happening, and at the level where the mystery lives, it has been replaced by something else entirely. In modern physics, there are no forces, there are fields. A field, in this context, means a quantity that exists at every point in space and time. Not a substance filling space, but a property of space itself, a number, or a set of numbers, attached to every location, everywhere, always. The electron is not a tiny ball. The electron is a ripple in an electron field that fills the universe. The photon is a ripple in the electromagnetic field. Every particle you have ever heard of is an excitation in some field, and the total inventory of fields is short. A handful of matter fields, a handful of force fields, and one Higgs field, and that is the world. What we call a force, then, is an interaction between fields. When two electrons repel, nothing reaches across the gap and pushes. What happens is that the electron field and the electromagnetic field are coupled. They talk to each other, and the outcome of that conversation, summed over every possible way it could occur, produces the behavior we describe as repulsion. The strength of a force is nothing more than how strongly two fields are coupled. A coupling constant is a measure of conversational volume. That is the modern picture, but it leaves the obvious question untouched. Why are there fields at all? Why does the universe carry a photon field around with it, rather than just having charged particles that ignore each other? The answer is one of the most beautiful and least famous ideas in all of science, and it begins with a woman who was not allowed to hold a job. In 1918, Emmy Noether, working at Göttingen, without a salary and without a professorship, because the university would not appoint a woman, proved a theorem that reorganized physics. Her result was this: every continuous symmetry of a physical system corresponds to a conserved quantity. If the laws of physics work the same today as tomorrow, symmetry under shifting time, then energy is conserved. If they work the same here as 1 meter to the left, symmetry under shifting position, then momentum is conserved. If they work the same regardless of which way you are facing, angular momentum is conserved. Conservation laws had been known for centuries as empirical rules. Noether showed they were not rules at all. They were shadows cast by symmetries. David Hilbert, arguing for her appointment to a faculty that kept refusing, is said to have asked what her sex had to do with it, since the Senate was not a bathhouse. She was appointed eventually, unpaid, lecturing under someone else's name. Now hold Noether's idea, and consider one more symmetry, an abstract one, with no obvious physical meaning. The quantum description of an electron involves a quantity that has a phase, in the way a wave has a phase. That phase is not directly measurable. Only differences between phases are. So you can rotate the phase of every electron in the universe by the same amount, and nothing observable changes. That is a symmetry. Noether's theorem says it must correspond to a conserved quantity, and it does. Electric charge is conserved because of it. So far, so tidy. Then in 1954, Chen-Ning Yang and Robert Mills asked a question that broke the whole subject open. What if you demand more? What if you insist that the phase can be chosen independently at every single point in space and time, that there is no universal reference, and each location gets to pick its own convention, and the physics must still come out the same? Picture space filled with compass needles. One at every point, everywhere, in every gap between every atom, an infinitely fine mesh of them, stretching in all directions. In the mild version of the symmetry, you may rotate all of them together, turn the whole mesh at once, and nothing changes. That is easy, and it costs nothing. Now try the strong version. Reach into the mesh and turn one needle, just one, by itself, leaving its neighbors where they were. Something has broken. The needle beside it is now pointing somewhere different, and any quantity that depended on comparing the two has changed. The physics noticed, and it should not have noticed, because you were only changing a convention, and conventions are supposed to be free. There is exactly one way to repair it. You must introduce a new field, spread through the whole mesh, whose job is to keep track of the mismatch between neighboring needles and absorb it. Whenever you turn a needle, this field adjusts, and the compensation is exact, and the physics is blind to what you did. The field is not optional. The symmetry cannot survive without it. And when you quantize that compensating field, when you ask what its ripples look like as particles, you get the photon. That is the gauge principle, and I would like to state it as plainly as I can, because it is genuinely one of the deepest things anyone has ever noticed. You do not put forces into the theory. You put a symmetry in, and the force falls out as the price of maintaining it. Light exists because the universe insists that a convention with no observable consequence should be freely choosable at every point in space. The photon is the accounting entry. Electromagnetism is a bookkeeping fee. Then it happens again. Feed the machine a slightly larger symmetry, a two-dimensional internal rotation, rather than a simple phase, and it hands you 3 force carriers instead of 1. Those are the W+, the W-, and the Z, and they are the weak nuclear force. Feed it a 3-dimensional version, the symmetry of what physicists call color, and it hands you 8 carriers. Those are the gluons, and they are the strong nuclear force. 1 idea, 3 forces. The counting is not adjusted after the fact to match observation. The number of carriers is fixed by pure mathematics, how many independent generators a given symmetry group has, and nature simply matched it. 1 for the phase symmetry, 3 for the 2-dimensional one, 8 for the 3-dimensional one, 12 force-carrying particles, and every one of them exists because a symmetry was demanded locally rather than globally. The idea nearly died in the room where it was first presented. When Yang gave a seminar on the work at Princeton in the spring of 1954, Wolfgang Pauli, who had explored something similar himself and abandoned it, interrupted almost immediately to ask what the mass of the new field was. It was not a polite question. Pauli knew the answer the mathematics gives, which is 0, and he knew that a massless charged carrier of that kind should have been easy to see and had never been seen. Yang had no reply. He sat down. Pauli pressed again. The objection was correct, and it took roughly a decade of further work to resolve, and the resolution turned out to be one of the most important ideas in physics in its own right. But on that afternoon, the gauge principle looked like an elegant construction that the world had already refused. There is a related point worth making now. because it will matter enormously in a moment. The photon's masslessness is not a lucky experimental fact, it is required. An unbroken symmetry of the kind we just described forces its carrier to have exactly zero rest mass, with no freedom to be otherwise, and experiment has been unable to find any deviation. The upper limit on the photon's mass sits somewhere around 10 to the minus 18 electron volts, which is to say, indistinguishable from nothing by an enormous margin. The same logic gives you charge conservation, not as an empirical regularity, but as a structural necessity. You cannot have this symmetry and violate charge conservation. The two are the same statement. The entire architecture of the Standard Model fits on a single line. Color symmetry times a two-dimensional weak symmetry acting on left-handed particles, times a phase symmetry, 3 groups, 12 carriers, all matter. Now sit with what that means for our 4-force problem, because the gauge principle does not resolve the mystery. It sharpens it into something much more uncomfortable. Before Yang and Mills, you could have looked at the 4 forces and concluded that they were simply 4 unrelated features of the world, the way a landscape contains rivers and mountains and forests without any of them being versions of the others. After Yang and Mills, that reading is unavailable. 3 of the 4 are not unrelated. They are 3 outputs of a single construction, differing only in which symmetry group you feed into it. They are 3 settings on the same machine, and they remain 3 separate groups, 3 separate coupling constants, with no relationship anyone can find between the numbers. The formula that describes the Standard Model has 2 multiplication signs in it, sitting between the 3 symmetries, and those signs mean nothing more profound than the word also, color symmetry, and also a weak symmetry, and also a phase symmetry. 3 things that came out of one idea, standing side by side, unconnected. If the idea is 1, the group ought to be 1. There ought to be a single larger symmetry that contains all 3 as pieces of itself, the way a single rotation in 3 dimensions contains rotations in each of the 3 planes. Then there would be 1 coupling constant instead of 3, and the 3 we measure would be fragments of it, related by the structure of the larger group, calculable rather than measured. That expectation has a name. It is called grand unification, and for about a decade in the 1970s, it looked like the most obvious thing in the world. We will get there, but before we do, there is a complication that the gauge principle appears, at first, to make worse rather than better. Because if all 3 of these forces come out of the same construction, and their carriers are produced by the same mathematics, then something needs explaining that the neat story just glossed over. Why does one of them reach across the entire universe, while the other 2 stop before they get out of the nucleus? Electromagnetism has no edge. An electric field weakens with distance, falling off as the inverse square, but it never reaches a point where it stops. The charge on an electron in your body is, in principle, felt by every charged particle in every galaxy in the observable universe. The effect is unmeasurably small at that distance, but it is not zero, and the difference between unmeasurably small and zero is the whole subject of this part. Gravity behaves the same way. Infinite range, inverse square, no edge. The other 2 stop. The strong nuclear force is finished at about 10 to the minus 15 meters, which is roughly the diameter of a proton. Move 2 protons apart by 3 proton widths, and the strong attraction between them has essentially vanished. The weak force is worse. It operates over something like 10 to the minus 18 meters, 1/1000th of a proton's width. If a proton were scaled up to the size of a football stadium, the weak force would reach about as far as a fingernail. 2 forces with unlimited reach, and 2 that cannot get out of an atomic nucleus. Where does the difference come from? In 1935, Hideki Yukawa worked out the answer, and it is one of those results that seems obvious once stated, and was not obvious at all before. If a force is carried by exchanging particles, then the question of range becomes a question about how far those particles can get. And quantum mechanics has something specific to say about that. The uncertainty principle allows the energy of a system to fluctuate, provided the fluctuation is brief enough. A larger borrowing must be repaid faster. Now, creating a force carrier out of nothing requires energy. At minimum, the energy locked up in its rest mass. If the carrier is massless, that minimum is zero, the loan can be arbitrarily small, and the repayment deadline can be arbitrarily far away. A massless carrier can travel forever. But if the carrier is heavy, the loan is large, the deadline is short, and the particles simply cannot get very far before the books have to balance. Yukawa's relation makes this quantitative. The range of a force is roughly Planck's constant, divided by the carrier's mass times the speed of light. Massless carrier, infinite range. Heavy carrier, short range, falling off exponentially beyond that characteristic distance. Run the numbers for the weak force, and everything clicks into place. The W boson has a mass of about 80.4 gigaelectronvolts, and the Z about 91.2. For comparison, an entire proton is about 0.938. A single weak force carrier weighs roughly 86 times as much as a proton, one force-carrying particle outweighing an entire nucleus of hydrogen by nearly 2 orders of magnitude. Put 80 gigaelectronvolts into Yukawa's formula, and you get a range of about 10 to the minus 18 meters, exactly what is observed. And here is the part that overturns the name. The weak force is not intrinsically weak. Its coupling, the volume of the conversation between the fields, in the language we used earlier, is actually comparable to electromagnetisms. If you probe it at energies high enough that 80 gigaelectronvolts is not a burden, the weak force is not feeble at all. It is roughly as strong as the electric force. It appears weak to us for the same reason a bridge appears impassable to someone who cannot afford the toll. The interaction is not rare because it is gentle. It is rare because the entrance fee is enormous compared with the energies available in ordinary matter. That distinction matters for everything that follows, so let me put it in the strongest terms available. One of the 4 fundamental forces is called weak because of an accident of the energy scale we happen to live at. Warm the universe up to a few hundred gigaelectronvolts and it stops being weak. The name describes our circumstances, not the force. Which raises the obvious follow-up. Why are the W and Z heavy when the gauge principle says carriers should be massless? That question is the one Pauli threw at Yang in 1954, and the answer took until the mid-1960s. The carriers are not born heavy. They acquire mass by moving through a field that fills all of space, the Higgs field, which has a non-zero value everywhere, including in what we call empty space. The symmetry that says the carriers must be massless is still there in the equations, perfectly intact. It is simply hidden by the state the vacuum happens to be in. The W and Z drag through the Higgs field and behave as though heavy. The photon does not couple to it in the same way and stays massless. The weak force is weak, therefore, because the vacuum of our universe is not empty in the relevant sense. Change the vacuum, and you change the force. Yukawa did not stop at the relation, he ran it backwards. The nuclear force was known to reach about a proton's width, so he inverted his own formula and predicted a carrier with a mass somewhere around 100 megaelectronvolts, a particle nobody had seen, whose existence and weight he had deduced purely from how far a force reached. In 1947, the pion was found, at roughly the predicted mass. Yukawa received the Nobel Prize in 1949, the first Japanese citizen to do so. The pion later turned out not to be the fundamental carrier of the strong force at all, but a composite leftover of something deeper, which makes this one of the stranger episodes in physics. A correct prediction confirmed by experiment, arrived at through reasoning that was only partly right. There is a consequence of weak force feebleness that you are relying on at this moment. The first step in the chain of reactions that powers the sun requires two protons to fuse and one of them to convert into a neutron, and only the weak force can perform that conversion. It is so improbable that an individual proton in the solar core waits, on average, on the order of 1 billion years for its turn. That bottleneck is the reason the sun burns slowly instead of detonating. A star is a hydrogen bomb held back by the reluctance of one of the four forces, and the 8.5 minutes of sunlight that will arrive tomorrow morning are the output of a process that is almost never allowed to happen. Now the strong force, which is short-ranged for an entirely different reason, and this is where the four begin to look genuinely unrelated rather than merely different. Gluons have no mass. Yukawa's formula would therefore predict infinite range, the same as the photon. It is wrong, and it is wrong because of a property no other massless carrier has. Gluons carry the strong force's own charge. A photon is electrically neutral, so photons ignore each other. Two beams of light pass through one another without interacting at all. Gluons are not color neutral, they pull on each other. The consequence is that the field between two strong charges does not spread out. Electric field lines from a charge fan out over an expanding sphere, which is exactly why the force falls as 1 over distance squared. The surface area of a sphere grows as the square of its radius, so the same field lines are diluted across more area. That inverse square law is really a statement about the dimensionality of space, not about electricity. Gravity obeys it for the same geometric reason. Gluon field lines refuse to fan out. Because the gluons attract each other, the lines collapse into a narrow tube running directly between the two charges, and the tube does not thin as it lengthens. Its energy grows roughly in proportion to its length. Pull harder, and instead of the force weakening with distance, you are simply paying more energy per additional meter, forever. This is confinement, and its consequence is stark. No free quark has ever been observed, and standard theory says none ever will be. The strong force is short-ranged, not because it fades, but because it will not let anything separate far enough to notice that it has faded. There is a leftover, and you are made of it. The protons and neutrons in your nuclei are individually color neutral, so in principle, the strong force between them should cancel entirely. It does not quite. A small residue leaks out, in the same way that electrically neutral atoms still feel a faint attraction to each other. And that residue is what binds nuclei together. Every atom in your body, heavier than hydrogen, is held together by the scraps of a force that has mostly cancelled itself. One more consequence, because it is the most personal one in this part. Since gluons interact with each other, the field inside a proton is not a passive background. It is a churning, self-sustaining structure with enormous energy in it. When you add up the masses of the 3 valence quarks inside a proton, they account for roughly 1% of the proton's total mass. The other 99% is the energy of the gluon field. You weigh what you weigh, almost entirely, because of field energy. Not because of the stuff, but because of the interaction. So we have 4 forces with 4 different reasons for behaving as they do. One reaches forever, because its carrier is massless. One stops after 1,000th of a proton, because its carriers were made heavy by the vacuum. One stops after a proton width, because its carriers will not stop pulling on each other. And one reaches forever, like the first, and yet is 36 orders of magnitude weaker. If somebody handed you that list cold, with no history attached, you would not immediately guess that any 2 of them were secretly the same thing. And yet, twice in history, somebody proved exactly that. In the spring of 1820, in a lecture room in Copenhagen, a professor named Hans Christian Ørsted was demonstrating an electric current to his students. On the bench nearby, for unrelated reasons, sat a compass. When he closed the circuit, the needle moved. It was a small motion, and it should not have happened. Electricity and magnetism were two separate subjects. They had separate histories. Magnetism reaching back to lodestones in antiquity, electricity to amber and static, and, more recently, to Volta's pile. They had separate practitioners, separate journals, separate laboratories. Nobody expected a wire carrying current to have any opinion about a compass, because a compass responds to magnetism and a wire carries electricity, and those were understood to be different phenomena that happened to share a general air of invisibility. The needle moved anyway. What followed was 4 decades of the most productive experimental work of the century, most of it done by Michael Faraday, a bookbinder's apprentice, with no mathematical training, who became the finest experimentalist of his age. Faraday found the converse effect. Move a magnet near a coil of wire, and you generate a current. He found that magnetism could rotate the plane of polarized light. He built the first electric motor and the first generator, and he developed, without equations, the idea that would eventually matter most, that the space around a magnet, or a charge, is not empty, but is filled with something, a set of lines of influence, a field. The field idea deserves a moment of its own, because it is the concept the whole of this video rests on, and it came from a man who could not do the mathematics. Faraday's contemporaries thought in terms of forces acting instantaneously across empty space, the way Newton's gravity was usually pictured, one object reaching out and touching another with nothing in between. Faraday could not accept it. He had watched iron filings arrange themselves into curves around a magnet too many times to believe that the space in between was doing nothing. So he proposed that the influence was in the space, continuously, everywhere, as a condition of the region rather than a relationship between the endpoints. It was regarded by many as a picturesque crutch for someone without algebra. Maxwell said explicitly that his own project was to translate Faraday's picture into mathematical form, and that when he did so, he found the two descriptions agreed. The crutch was the correct physics. Every field we have discussed tonight, electron field, gluon field, Higgs field, is a descendant of a bookbinder's apprentice refusing to believe that empty space was empty. By the 1860s, the two subjects were clearly entangled. They were still two subjects. James Clerk Maxwell took Faraday's picture and gave it mathematics. His original formulation ran to 20 equations in 20 variables. The compact set of 4 that students learn today is Oliver Heaviside's rewriting from the 1880s, using vector calculus that Maxwell did not have. And what Maxwell's equations did was not merely describe both phenomena at once. They made the separation impossible. In his system, there is no electric field and magnetic field. There is one electromagnetic field, with 2 aspects, and every equation involves both. Change one, and the other changes. They are not partners. They are the same object. Then the equations did something nobody had requested. Maxwell noticed that his system permitted a self-sustaining disturbance. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. And if you set that up correctly, the pattern can propagate through empty space, each aspect regenerating the other, indefinitely, with no medium required and no charges present. A wave, and the equations specified its speed, not as a free parameter, but as a fixed combination of 2 constants that had been measured in laboratories by people doing entirely unrelated experiments with wires, coils, and glass jars. He calculated the number. It came out at roughly 300,000 kilometers per second. That speed was already known. It had been measured astronomically by Romer in the 1670s from the timing of Jupiter's moons, and terrestrially by Fizeau in 1849 with a rotating toothed wheel and a mirror on a distant hill. It was the speed of light. Nobody had been trying to explain light. Maxwell had been trying to tidy up the relationship between two laboratory phenomena, and the tidying up produced optics as a free gift. Light was not a separate subject either. Light was an electromagnetic wave, the thing his equations said must exist, traveling at the speed his constants demanded. I want to be precise about why this episode matters so much for the story we are following, because it is easy to hear it as a nice piece of history rather than as the template for everything since. A real unification does not simply rename two things as one. Anyone can do that. It costs nothing and predicts nothing. A real unification forces the appearance of something you were not looking for, and that something is testable. Maxwell's produced light, and then produced radio. Heinrich Hertz generated and detected electromagnetic waves at frequencies far below visible light in 1887, because the equations said such waves must be possible, and within 2 decades, that discovery had become an industry. The unification paid, and it kept paying, and it is still paying every time your phone finds a signal. Hertz, asked what use his waves might be, is supposed to have answered that they were of no use whatsoever, just something that proved Maxwell right, and that the eye could not see. He was describing the entire future of telecommunications. This is worth remembering whenever anyone asks what the point of a unification is. Nobody in 1865 could have said what the practical value of joining electricity to magnetism might be. The answer turned out to be every wireless signal that has ever been sent. There is a deeper sense in which the two were always one, and it did not become clear until Einstein. Consider a charge sitting still. It has an electric field and no magnetic field. Now walk past it. From your moving frame, that stationary charge is a current, and a current produces a magnetic field. So in your frame there is magnetism, where in the other frame there was none. Nothing physical changed. You changed velocity. What one observer calls a magnetic field, another calls partly an electric field, and the split between the two depends on who is asking. Special relativity does not merely relate them, it says that the division into electric and magnetic is a description of your motion, not a description of the world. That is what a completed unification looks like from the inside. Not two things joined, but one thing that had been described twice by people standing in different places. And this was not even the first time. Newton had done it 2 centuries earlier, and we tend to forget it because the result is now so ordinary. Before the Principia, the physics of things falling on Earth and the physics of things moving in the heavens were separate disciplines with separate rules, inherited from Aristotle, and the separation was not a casual assumption. It was doctrine. The celestial region was made of different material and obeyed different laws, because the heavens were perfect and the sublunary world was not. Newton proposed that the force pulling an apple down and the force holding the moon in its orbit were the same force, with the same law, differing only in distance. He then showed that the numbers worked. Terrestrial and celestial mechanics stopped being 2 subjects that afternoon. So by the middle of the 20th century, physics had a track record. Twice, it had reduced the count. Twice, the reduction had produced something new that could be checked. Twice, the check had come back positive. It would be difficult to overstate how much confidence that record generated. If you were a physicist in 1960 and you looked at the 4 fundamental forces, you did not see 4 permanent features of nature. You saw a number that had been coming down for 300 years and was clearly going to keep coming down. The only questions were which pair would fall next and how long it would take. The answer to the first question came quickly. It would be electromagnetism and the weak force, and the argument for pairing them would begin from a coincidence of numbers that nobody could quite ignore. But before that story, we need to understand what the weak force actually is, and I should warn you that of the 4, it is by some distance the strangest. It does not merely push and pull. It changes what things are, and it does so in a way that violates a symmetry so basic that when the violation was first proposed, most of the physics community assumed the proposers had made an error. 3 of the 4 forces move things around. The weak force turns them into other things. That distinction is easy to say quickly and worth slowing down for, because it makes the weak force categorically different from its neighbors in a way that strength and range do not capture. Electromagnetism can accelerate an electron, bind it into an atom, knock it loose again, but at the end of every one of those interactions, the electron is still an electron. The strong force can bind quarks, confine them, tear a new pair out of the vacuum, but an up quark remains an up quark throughout. Gravity moves everything and changes nothing about what anything is. The weak force converts a down quark into an up quark. It converts a muon into an electron. It changes the identity of the particle it touches. In the accounting of the Standard Model, particles come in what are called flavors, and the weak interaction is the only thing in the universe that can change a particle's flavor. It is not a force in the sense of pushing, it is a transmutation. You are alive because of it. When a neutron inside a nucleus turns into a proton, emitting an electron and an antineutrino, in the process called beta decay, that is a down quark becoming an up quark, mediated by a W boson. That reaction is what makes some elements radioactive, and it is what allows nuclear reactions in stars to progress up the periodic table. Without it, the sun's fusion chain never starts, no heavy elements are built, and the universe stays a thin mixture of hydrogen and helium indefinitely. The story of how the weak force was discovered is a good demonstration of how strange it is, because it announced itself as a bookkeeping failure. Early in the 20th century, physicists studying beta decay found something wrong. When a nucleus decays and emits an electron, energy conservation says the electron should come out with a specific, predictable energy, the difference between the initial and final states, every time. Instead, the emitted electrons came out with a whole spread of energies, from nearly zero up to the expected maximum. Energy appeared to be leaking away. The situation was serious enough that Niels Bohr was prepared to abandon energy conservation for these processes. In 1930, Wolfgang Pauli proposed an alternative that he himself described in a letter as a desperate remedy. Perhaps a second particle was being emitted alongside the electron, carrying off the missing energy. A particle with no charge, essentially no mass, and almost no willingness to interact with anything. He apologized in the same letter for having proposed something that could not be detected. It took 26 years. The neutrino was finally observed in 1956 by Clyde Cowan and Frederick Reyners, using a detector placed beside a nuclear reactor, because a reactor produces neutrinos in overwhelming numbers, and overwhelming numbers is what you need. Roughly 100 million neutrinos from the sun are passing through your body every second as you lie there. Over a human lifetime, the number that will actually interact with any atom in you is somewhere in the region of 1. The weak force is that reluctant. It is worth lingering on that image for a moment, because it is one of the quieter, strange facts about the night you are lying in. The sun is on the other side of the planet right now, and its neutrinos are not stopped by the planet. They pass through 8,000 miles of rock and iron, as though it were open air, arrive at the underside of your bed, pass through the floor, through the mattress, through you, through the ceiling, and continue outward into space. Hundreds of millions of them, every second, all night, every night of your life. Nothing registers, nothing warms. There is no sensation to have, because the interaction that would produce one almost never happens. The weak force is the reason you are transparent to the sun. And then, In 1956, the weak force did something considerably worse than being shy. It broke a symmetry that everyone had assumed was structural. Parity is the symmetry between left and right, the claim that the laws of physics, run in a mirror, look the same. It was not regarded as a hypothesis. It was regarded as the sort of thing that did not need testing, on the grounds that the universe had no way of knowing which was which. Electromagnetism respects it, gravity respects it, the strong force respects it. Sung Dao Li and Chen Ning Yang, examining a puzzle in the decay of certain particles, noticed something remarkable. Parity conservation had been carefully tested in strong and electromagnetic interactions, and never once tested in weak interactions. Everyone had assumed it. Nobody had checked. Qian Xiongwu checked. She was an experimentalist at Columbia, and the experiment she designed was brutally direct. Take cobalt-60, which undergoes beta decay, cool it to a few hundredths of a degree above absolute zero, and use a magnetic field to align the nuclear spins so that all the nuclei are pointing the same way. Then count which direction the emitted electrons go, relative to the spin. If parity holds, the count must be equal in both directions, because a mirror image of the experiment has to look like a valid experiment. The cryogenics required were beyond what Columbia could provide, so the work was done at the National Bureau of Standards in Washington over the winter of 1956 into 57, in conditions that required the apparatus to be rebuilt more than once. The result was not a marginal asymmetry. The electrons came out preferentially in one direction. Strongly, the universe distinguishes left from right, and it does so through one of the four forces and only that one. The reaction in the field was close to shock. Pauli had written shortly before, in a letter, that he did not believe God was a weak left-hander. Richard Feynman lost a bet. Li and Yang received the Nobel Prize in 1957, an unusually fast recognition. Wu did not receive it, a decision still discussed with discomfort. Then it got stranger. Follow-up work established that the weak force does not merely prefer one-handedness, it couples exclusively to left-handed particles and right-handed antiparticles. Maximal violation, not a bias, a total exclusion. This is why the mathematical description of the Standard Model has to specify a symmetry that acts only on the left-handed components of matter fields. That is what the subscript in the formula means, the one that reads SU2, left. The weak force is written with a handedness built into its foundations, and nothing anywhere explains why. Nor was that the last asymmetry the weak force turned out to be hiding. In 1964, James Cronin and Val Fitch found that the weak interaction also violates a combined symmetry called CP, roughly the symmetry between a particle and its mirrored antiparticle. The violation is tiny, a few parts in 1,000 in the decays of neutral kaons, nothing like the total lopsidedness of parity violation. But its consequences are enormous, because a universe in which matter and antimatter behave identically ends up containing equal amounts of both, and equal amounts annihilate completely. The existence of anything at all requires some process that treats matter and antimatter differently. The weak force is currently the only known one, and even its known violation is far too small to account for the amount of matter that survived. That gap remains open. And there is one more item, which arrived much later. The original Standard Model assumed neutrinos were massless, because no mechanism gave them mass, and no experiment demanded it. Then, over the 1990s and into the 2000s, detectors found that neutrinos change flavor in flight. A neutrino created as one type arrives as another, and that is only possible if they have mass. Small mass, but not zero. The leading explanation for why those masses are so extraordinarily small ties them, through what is called the seesaw mechanism, to a very heavy scale far above anything we can reach. The lightness of the lightest particles may be a fingerprint of the heaviest physics there is, which is a hint worth carrying with us into the next few parts. Sit with that against the background of everything we have said so far. 3 forces are outputs of one construction, but one of those 3 is handed and the other 2 are not. One of those 3 changes what particles are, and the other 2 do not. One of those 3 has heavy carriers, and the other 2 have massless ones. If somebody claimed that a phenomenon which changes particle identity, discriminates between left and right, works only over 1,000th of a proton's width, and is carried by objects 80 times heavier than a hydrogen nucleus, was secretly the same force as the one that makes your lamp glow, you would want to see the argument. The argument exists, it is correct, and it was confirmed twice, first by finding a phenomenon nobody had ever observed, and then by manufacturing particles that had never existed on Earth. That is where we are going next, and it is the high water mark of this entire subject. For a period of about 10 years, from the mid-1970s into the mid-80s, physicists had every reason to believe they were 3 or 4 steps from the end of the road. The argument that electromagnetism and the weak force are one thing began, as these things often do, with a piece of mathematics that was almost right and obviously broken. Between 1961 and 1968, working partly together and partly independently, Sheldon Glashow, Abdus Salam, and Steven Weinberg built a theory in which a single symmetry, the 2-dimensional weak symmetry, combined with a phase symmetry, generates 4 carriers rather than the 3 you might expect. 3 of those carriers pair up into the W+, the W-, and the Z, and the 4th comes out as the photon. Electromagnetism and the weak force are not 2 forces that resemble each other. In this picture, they are 2 different mixtures of the same underlying 4 fields, and the proportions of the mixing are set by a single number, the weak mixing angle. The theory had a fatal-looking problem at the outset. The symmetry demands massless carriers, and the W and Z are demonstrably heavy. That was Pauli's objection from 1954, returning in a new suit. The resolution came through the mechanism we touched on earlier, a field filling all of space, with a non-zero value even in the vacuum, which the W and Z drag through and the photon does not. The symmetry is not destroyed. It is hidden by the state the vacuum is in. The equations remain symmetric. The world they describe does not look symmetric, because the vacuum has picked a direction. That resolution was elegant. But elegance is not evidence. And what made the electroweak theory science, rather than mathematics, was that it predicted something no one had ever seen. Every weak interaction known at the time involved a change of identity. A neutron becomes a proton. A muon becomes an electron. Something turns into something else, and the charge moves around, which is why these are called charged currents. The electroweak theory required, in addition, a neutral one, an interaction mediated by the Z, in which a neutrino strikes a particle, bounces off, and remains a neutrino. Nothing changes identity. Momentum is transferred, and everybody walks away as themselves. Nothing in the existing catalogue of weak processes worked that way. If the theory was right, this had to exist. If it did not exist, the theory was dead. In 1973, the Gargamel bubble chamber at CERN found it. Gargamel was a 20-ton cylinder filled with liquid freon, photographed continuously, and what the collaboration was looking for were events in which a neutrino beam produced visible tracks with no outgoing muon, the signature of a neutrino that had struck something and remained a neutrino. The analysis was agonizing, because the same photograph could be produced by stray neutrons wandering in from the surrounding material, and the collaboration spent months arguing over whether the effect was real. It was real. The neutral current existed. The 1979 Nobel Prize in Physics went to Glashow, Salam, and Weinberg for their contributions to the unified theory of the weak and electromagnetic interaction, and the citation named "The Prediction of the Weak Neutral Current" explicitly. The unification had done what a real unification does. It had forced the appearance of something nobody was looking for, and the something had turned up. But there was a much harder test available, and it was the obvious one. If the W and Z are real particles with definite masses, then given enough energy, you should be able to make them. The masses predicted were around 80 and 90 gigaelectronvolts, which in the 1970s was far beyond the reach of any existing machine. In 1976, Carlo Rubbia, Peter McIntyre, and David Klein proposed a way around the problem. Rather than building a new accelerator, take CERN's existing superproton synchrotron and convert it from a machine that accelerated protons into a machine that collided protons with antiprotons head-on. Colliding beams give you far more usable energy than firing a beam at a stationary target. The difficulty was antiprotons. You have to manufacture them, collect them, store them, and keep them in a tight enough bunch to be worth colliding. And antiproton beams produced by conventional means are hopelessly diffuse. The solution was Simon van der Meer's, and it is one of the most ingenious pieces of engineering in the history of accelerators. It is called stochastic cooling. As the beam circulates, a sensor at one point in the ring measures the statistical wander of the particles, how far, on average, this bunch is straying from the ideal path. That information is sent straight across the diameter of the ring, arriving before the particles do, and a corrective kick is applied on the far side. Repeat, millions of times per second, and the beam tightens. Van der Meer had developed the technique in the 1970s for other purposes entirely. Now it made the impossible experiment possible. The machine ran from 1981. Two enormous detectors watched the collision points. UA1, led by Rubbia, and UA2, led by Pierre Dariulla, deliberately built as rivals so that neither could claim a discovery the other could not confirm. Now picture the CERN auditorium on the 20th of January, 1983. The room is past capacity. People are standing along the walls and sitting in the aisles because word has gone around the site that Rubbia has something. He has been arguing for this machine for 7 years. An entire accelerator was rebuilt on the strength of his conviction. A cooling technique had to be invented. Hundreds of physicists have spent years of their lives on detectors the size of houses. And what he puts up, in the end, is 6 events. 6 collisions out of a billion, in which the debris pattern shows a high-energy electron flying off one way and a great deal of missing momentum going the other. The signature of a W boson that came into existence for a fraction of a second and decayed. 6 pictures on a screen in a crowded room in Geneva, and the mass they imply is about 80 gigaelectronvolts, which is what the theory said 15 years earlier. The following afternoon, Luigi Di Lella stands up for UA2 and shows 4 more, found independently, in a different detector, by a group that has every professional incentive to disagree. They do not disagree. CERN announced the discovery to the world on the 25th of January. The Z followed within a few months, its mass close to 91 gigaelectronvolts, again as predicted. Rubbia and van der Meer shared the Nobel Prize the following year, in 1984, an interval of roughly 18 months between the discovery and the prize, which is nearly unheard of. The last piece of that story arrived almost 3 decades later. The field responsible for hiding the symmetry, the one the W and Z drag through, should itself have a particle associated with it, a ripple in the field like any other. Finding it required a machine, an order of magnitude beyond the one that found the W, and on the 4th of July, 2012, CERN announced that both of the Large Hadron Collider's general-purpose detectors had found a new particle at about 125 gigaelectronvolts with the right properties. The mechanism that makes the weak force weak was confirmed 48 years after it was proposed. Every particle in the electroweak sector had now been produced, measured, and found where the theory said it would be. There is a caveat buried in this triumph that is usually left out of the popular telling, and we need it, because the whole of the rest of tonight depends on it. Electroweak unification unified the description. It did not unify the numbers. The theory still contains two separate symmetry groups with two separate coupling constants related by the weak mixing angle, and that angle is not predicted by the theory. It is measured. Physicists went into laboratories, determined its value, and inserted it by hand, exactly as with every other free parameter we have discussed. What the electroweak theory achieved was to show that two forces are aspects of one structure. What it did not achieve was to explain why that structure has the strengths it has. That distinction is the difference between the unification everyone celebrates and the unification everyone is still waiting for. And it is why the next step, the one that would fold in the strong force as well, was never going to be a matter of tidying up. It required something more ambitious. Not two groups joined by a mixing angle, but one group, with one coupling, from which all three of the measured numbers could be calculated. So consider where physics stood at that moment. Two forces that had looked completely unrelated, one that lights the world and reaches forever, and one that changes what particles are, prefers left over right, and stops before it leaves a nucleus, had been shown to be two faces of one interaction. The proof had arrived twice. First as a phenomenon nobody had ever seen, then as particles that had not existed anywhere on Earth until we made them. The predicted masses matched the measured masses. The record of unification now stood at 3 attempts and 3 successes, spread across 3 centuries. The remaining task looked, from that vantage point, entirely tractable. 2 of the 4 were now won. The strong force was described by the same kind of mathematics, differing only in which symmetry you fed the machine. Nobody thought the last step would be easy, but nobody serious thought it would fail. There was one more piece to place before that final step could be attempted, and it concerned the strong force, which, on close inspection, turns out to behave in a way that no other force in nature does, and which contains the single most counterintuitive fact in this entire subject. Pull 2 of its charges apart, and it does not get weaker. Every force you have direct experience of weakens with distance. Move away from a magnet, and the pull fades. Move away from a planet, and the weight drops. This is so deeply built into our expectations that it barely registers as a claim about physics. It feels like a fact about the meaning of the word distance. The strong force does the opposite, and I want to take you inside a proton, so you can feel the shape of it. Imagine you could reach in and take hold of one quark, not a metaphorical grip, an actual hold on one of the 3 valence quarks in a proton in your fingertip, with the ability to pull. You begin to draw it out. At first, nothing surprising. The quark resists, the way anything bound resists. You pull harder, it moves a little. But the resistance does not fall away as you make progress, which is what every intuition you have says should happen. It stays constant. You are not climbing out of a well that gets shallower near the rim. You are dragging something across an infinite flat plane, and the effort per centimeter never drops. What is happening between your quark and the 2 you left behind is that the gluon field has collapsed into a narrow tube, a flux tube, a taut rope of color field, running directly from your quark to the others. It does not spread out, because gluons pull on gluons, and the energy stored in that rope grows in direct proportion to its length. Pull for twice as long, and you have paid twice as much. So you pull harder still, and now, something in the arithmetic turns over. The energy you have poured into that stretched rope reaches the point where it equals the rest mass energy of a new quark and antiquark pair, and at that instant, the vacuum obliges. The rope snaps, and where it snaps, a new quark and a new antiquark appear out of the energy you supplied. You look at what is now in your hand. It is not a bare quark. It is a quark bound to the new antiquark, a meson, a perfectly respectable composite particle. And back where you started, the proton has healed itself with the new quark, and is a proton again. You put in an enormous amount of energy to isolate a quark, and the universe spent your energy manufacturing new particles, rather than letting you have one on its own. Try again with more force, and you get the same answer, more emphatically. There is no amount of pulling that works. In the entire history of experimental physics, spanning collisions at energies millions of times higher than anything in this thought experiment, no free quark has ever been observed. That is confinement. It is not a practical difficulty. It appears to be a law. A word about the charge itself, because the name is a joke that stuck. Electric charge comes in one variety with two signs. The strong forces charge comes in three varieties, and when physicists needed labels, they borrowed red, green, and blue. Not because quarks have colors, which they emphatically do not, but because three things that combine to give something neutral is a familiar arrangement from the way human vision works. A proton contains one quark of each, and the combination is color neutral, which is why a proton can exist as a free particle, while a lone quark cannot. Every observed particle in the universe is color neutral. That is not a rule imposed from outside. It is what confinement means when you write it as a statement about which combinations are allowed to be alone. The strength of the strong force is quantified by a number called alpha S, and unlike its electromagnetic cousin, it changes dramatically over the range we can measure. At the energy of the Z boson, around 91 giga-electronvolts, alpha S is about 0.118, not much larger than the electromagnetic coupling at the same energy. Drop down to around 1 giga-electronvolt, roughly the mass of a proton, and it climbs toward 1. The force that dominates at nuclear scales is not overwhelmingly strong at all energies. It is overwhelmingly strong at ours. There is a version of the universe in which that stops being true, and it existed. In the first few microseconds after the Big Bang, the temperature was high enough that quarks and gluons were not confined into particles at all. They moved as a fluid, a quark-gluon plasma, and everything that now sits inside protons and neutrons was, for a moment, loose. That state has since been recreated on Earth, briefly, by smashing heavy nuclei together at the relativistic heavy ion collider and at the Large Hadron Collider, producing droplets of matter at trillions of degrees that behave as very nearly the most perfect fluid ever measured. Confinement, in other words, is not eternal either. It switched on as the universe cooled, exactly as the distinction between the electromagnetic and weak forces did. Now for the second half, which is where the strong force stops being merely exotic and becomes the reason this whole story has a hope of resolving. Because if the force stays constant as you pull things apart, what happens when you push them together? It gets weaker. This is asymptotic freedom, and it was discovered in 1973 by David Gross and his graduate student Frank Wilczek at Princeton, and independently by David Politzer, a graduate student of Sidney Coleman at Harvard. Their papers were published back-to-back in the same issue of Physical Review Letters. The three shared the Nobel Prize in 2004. The result was genuinely unexpected, and Gross has said since that he set out to prove the opposite. The prevailing belief was that no quantum field theory could behave this way. What makes it possible is that peculiar property of gluons. Again, they carry the charge they mediate. In electromagnetism, the vacuum around a charge fills with virtual electron-positron pairs, which orient themselves and partially shield the charge. So the closer you get, the more of the true charge you see. In the strong force, the gluon self-interaction produces the reverse effect. It smears the charge outward rather than shielding it inward, so the closer you get, the less you feel. The consequence is that quarks inside a proton, when probed hard and briefly, behave almost as though they were free particles rattling around in a bag, which is exactly what deep inelastic scattering experiments had found at Stanford in the late 1960s, to everyone's confusion at the time. The same quarks, left alone, cannot be separated by any force available in the universe. Both facts are true of the same objects. Free when you look closely, imprisoned when you step back. There is a consequence of all this that is personal, and I think it is the most underappreciated fact in physics. Add up the masses of the three valence quarks in a proton, 2 up quarks and a down quark. The total comes to roughly 1% of the proton's mass. Where is the other 99%? It is the gluon field. It is the energy of that churning, self-interacting, confined field, converted into mass by the relation between the two. Your body weighs what it weighs almost entirely because of the energy stored in an interaction, not because of the amount of substance present. If you could somehow switch off the strong force's self-interaction while keeping everything else, you would lose 99% of your mass. You are not mostly made of matter. You are mostly made of a force. I should add that the strong force has a mystery of its own that we will not have time to open properly tonight, but which deserves naming, because it is the same species of puzzle as everything else we are discussing. Nothing in the theory prevents the strong force from violating the matter-antimatter symmetry the way the weak force does. There is a parameter in the equations, free to take any value, that controls how much it does so. Measurements of the neutron say that parameter is 0, or within about 1 part in 10,000 million of 0. It could have been anything. It is essentially exactly nothing, and nobody knows why. Another number, measured rather than derived, sitting in the theory with no explanation attached. And now, finally, we can put the two halves of this part together into the fact that reopened the whole unification program. If the strong force gets weaker at high energy, and if electromagnetism, as we will see, gets stronger at high energy, then the two are moving toward each other, not metaphorically, numerically. Plot the strength of each force against the energy at which you measure it, and one line rises while the other falls. Lines that move toward each other meet somewhere. The question is whether they meet at a single point, all three of them together, or whether they merely cross each other at different places like traffic on a busy afternoon. If all three arrive at the same value, at the same energy, that is not a coincidence. That is what you would see if the three forces were fragments of one force, appearing separate only because we live at low energy, the coupling constants of one interaction, split apart by a cooling universe and drifting since. If they miss, then either the picture is wrong or something else is out there that we have not accounted for. This calculation was first done properly in the mid-1970s, and the answer it gave was close enough to keep several generations of physicists working on the same problem for the next 50 years. There is a phrase in physics that quietly stopped being true about 60 years ago, and almost nobody outside the field has been told. The phrase is coupling constant. They are not constant. The strength of a force depends on the energy at which you measure it. This is not a statement about experimental error or about the difficulty of measurement. The number itself changes, systematically and predictably, and the reason is that empty space is not empty. Place a single electron in a perfect vacuum. Around it, continuously, pairs of virtual particles flicker into brief existence and vanish. Electron and positron, appearing on borrowed energy and repaying it before anything can notice. While they exist, they respond to the electron's charge. The positive members of each pair drift slightly inward, the negative members slightly outward. The result is a cloud of polarized vacuum surrounding the charge, partially cancelling it. So when you measure the electron's charge from far away, you are not measuring the electron, you are measuring the electron plus its screening. Get closer, which in practice means probing with higher energy, and you penetrate more of the cloud and see more of the true charge. The measured coupling rises. The numbers are concrete. At the low energies of everyday chemistry, the electromagnetic coupling is the familiar one, over 137. Measure it in collisions at the mass of the Z boson, around 91 giga-electronvolts, and it is closer to 1 over 128. That rise has been observed directly at the electron-positron collider at CERN. Electromagnetism genuinely is stronger when you look at it harder. The strong force runs the other way, for the reason we established. Gluons interact with each other, so the vacuum around a color charge does not screen it, but spreads it, and probing closer means feeling less. The weak coupling has its own behavior, drifting slowly. The direction of that running was not a minor technical detail when it was found. The quantity that governs which way a coupling moves is called the beta function, and for a long time it was believed that it could only have one sign, that every quantum field theory must get stronger at short distance, as electromagnetism does. Gross has said that he began the calculation intending to demonstrate exactly that, and to close off a line of speculation for good. The result came out with the opposite sign. Sometimes the most important thing a physicist does is fail to prove what they set out to prove. Now do the thing that everyone who understands this immediately wants to do. Take the three couplings, measured to high precision at energies we can reach, and use the equations that govern their running to extrapolate them upward, not to twice the energy, upward by a dozen orders of magnitude, into a regime no experiment has ever touched, to see where the lines are heading. The electromagnetic line rises, the strong line falls, the weak line drifts between them, and as you climb, they converge. They come together in the region of 10 to the 15th to 10 to the 16th giga-electronvolts. Three quantities, measured in laboratories on Earth by completely different methods, extrapolated across 12 orders of magnitude, and they head for the same neighborhood. That convergence is the single most suggestive piece of numerical evidence in this entire subject. If the three forces are fragments of one force, and if that one force has one coupling strength, then below the energy at which the larger symmetry breaks apart, the three fragments would separate and drift, and running them backwards should bring them home. What we observe is exactly that pattern. There is only one problem, and it is the one that gives this part its name. The lines almost meet. In the plain standard model, with only the particles we have actually detected, the three lines do not pass through a single point. They pass close. They cross each other pairwise at slightly different energies, within a few % of one another, on a scale where a factor of 100 would not be surprising, and then they separate again. It is a near miss, not a triumphant intersection, not an obvious failure, an almost. For decades, that almost has functioned as an invitation, because you can fix it. If there are additional particles out there, at energies not too far above what we have explored, they change the way the couplings run. Every particle that can be produced at a given energy contributes to the vacuum's response above that energy. Add the right extra content, and the three lines can be nudged into agreement. The candidate that works best is supersymmetry, the proposal that every known particle has an undiscovered partner, differing from it in a specific technical way. Put those partners in at around the scale of 1,000 giga-electronvolts and recompute, and the three lines meet with remarkable precision at about 2 times 10 to the 16th giga-electronvolts. For 20 years, that was quietly the strongest argument for supersymmetry in existence. Not a detection, a graph, in which three lines that missed suddenly met. And unification was not even the main reason people liked it. Supersymmetry arrived carrying three separate gifts. It fixed the running of the couplings. It stabilized the mass of the Higgs against quantum corrections that should otherwise have made it enormous, a problem we will come to shortly. And it supplied, without being asked, a natural candidate for dark matter in the form of its lightest new particle, which would be stable and would interact only feebly. One idea, three unsolved problems, three solutions. In physics, that kind of convergence is usually taken as a sign that you are on the right track, because it is very difficult to be accidentally right about three things at once. Let me step back for a moment and restack what we have, because we are about to leave the comfortable part of this story, and the pieces matter. We have four forces. Three of them come out of one construction, differing only in which symmetry you feed it. Their strengths are three measured numbers, with no derivation. Those numbers are not fixed. They change with energy, in a way we can calculate and have confirmed. Extrapolate them up, and they head toward one another and nearly converge at an energy 12 orders of magnitude beyond any machine we could build. Adding hypothetical particles at a reachable energy turns the near convergence into an exact one. That is the state of the argument. There is one caution to attach before we proceed, and it is honest rather than deflating. The running is logarithmic, which means that enormous changes in energy produce only modest changes in coupling. That cuts both ways. It is why an extrapolation across 12 orders of magnitude is even conceivable. The lines move slowly and predictably. But it is also why small uncertainties in the low-energy measurements are stretched into large uncertainties at the far end, and why judgments about whether three lines truly meet or merely graze each other depend on precision at the third decimal place of quantities measured on Earth. This is a long lever, and long levers amplify everything, including error. We will come back to what happened to that argument, because something did happen to it, and it was not good. But first I want you to look at the number itself, because the number is doing something to this subject that no amount of theoretical cleverness can undo. 10 to the 16th giga-electron volts. The Large Hadron Collider, a ring 27 kilometers around, buried 100 meters under the border between France and Switzerland, the largest and most expensive scientific instrument ever built, collides protons at 13.6 tera-electron volts. That is about 1.4 times 10 to the 4th giga-electron volts. The gap between the machine and the target is 12 orders of magnitude, a million times. To reach the unification scale directly, with anything resembling current accelerator technology, you would need a machine larger than the solar system. That is not a rhetorical exaggeration. It is roughly what the scaling gives you. There is no plausible engineering path, no clever trick, no sequence of incremental improvements that closes that gap. The place where the three forces become one, if they do, is permanently beyond the reach of direct experiment. That is the situation. There is a scale at which the great question of this subject is answered, and physics can see it, and cannot go there, and never will. So the argument turns on indirect evidence. If the three forces really do become one at 10 to the 16th giga-electron volts, does anything follow that we could check down here, at the bottom of the energy ladder, with instruments we can actually build? It does. One thing follows, and it is beautiful, and it is testable, and it is the reason this whole story has an experimental chapter, rather than remaining a debate about graphs. Remember what I said at the beginning of tonight, half in passing. 4 is not a natural number for a universe to choose. We are now in a position to see how sharp that observation is. Because if the convergence means what it appears to mean, then 4 was never the answer. There were never 4 forces. There was one, at a temperature we cannot reach, and then the universe cooled, and the one shattered into pieces, and we are standing in the debris, counting fragments, and calling the count a fundamental fact about nature. If that is true, the number 4 is not a property of physics. It is a property of the era we happen to live in. And there is a way to find out. In February of 1974, Howard Georgi and Sheldon Glashow published a paper 4 pages long in physical review letters. Its title was direct to the point of arrogance: Unity of all elementary particle forces. Their proposal was the obvious one, done properly. The three symmetry groups of the Standard Model, they suggested, are not the fundamental structure. They are three fragments of a single larger group, which they identified as the simplest one big enough to contain all three. At high energy, that larger symmetry is intact, and there is one force with one coupling strength. As the universe cooled, it broke apart, and the three pieces have been drifting apart ever since. The proposal explained something immediately, and the something it explained is a coincidence so glaring that most people have never noticed it is a coincidence. The electron's electric charge is exactly equal and opposite to the proton's. Not approximately. Experiments looking for any residual charge on bulk neutral matter constrain the difference to less than about 1 part in 10 to the 21st, and there is no reason for it. An electron is a fundamental particle, indivisible as far as anyone can tell, a member of the lepton family. A proton is a composite object made of 3 quarks, members of an entirely different family, bound by a force the electron does not even feel. 2 utterly different kinds of object, and their charges match to 21 decimal places. In the Standard Model, this is not explained. It is simply recorded. The charges are assigned by hand, and they happen to work out. In the unified picture, it is forced, because in a single larger symmetry, quarks and leptons sit together in the same families. They are not different kinds of thing. They are different states of one kind of thing, related by the symmetry, and the symmetry constrains their charges to be exactly what they are. The neutrality of every atom in your body, which is the reason chemistry exists, and the reason you are not being torn apart by electrostatic repulsion at this moment, drops out of the structure automatically. That is a serious argument, but it carries a price, and the price is the entire drama of the next 50 years. If quarks and leptons are in the same family, related by a symmetry, then there must be carriers that convert one into the other. That is what a symmetry means. The members of a family can be rotated into each other, and rotating them is done by exchanging a boson. These hypothetical carriers were named X and Y, and their masses would be at the unification scale, which is to say, unimaginably heavy. And if a quark can turn into a lepton, then the proton is not stable. Inside a proton, 2 quarks can, extremely rarely, exchange one of these enormously heavy carriers and convert into a positron and a pion. The proton, the most durable composite object known, the thing every atom in the universe is built around, a particle that has been assumed permanent since the concept existed, must eventually fall apart. Minimal versions of the theory put its lifetime somewhere around 10 to the 30th years. That sounds like the end of testability. The universe is only about 14,000 million years old. Waiting 10 to the 30th years for one proton to decay is not an experiment anybody is going to run. But you do not have to wait for one. That is the trick, and it is a genuinely lovely piece of reasoning. Decay is a matter of probability per unit time. If the average lifetime is 10 to the 30th years, then in any given year, roughly 1 proton in 10 to the 30th will decay. So do not watch 1 proton. Watch 10 to the 33rd of them, all at once, and you should see hundreds of decays a year. 10 to the 33 protons is about 10,000 tons of water. So they built it. 2 collaborations, on opposite sides of the world, constructed enormous tanks of water, deep underground. Deep, because a kilometer of rock filters out the cosmic ray muons that would otherwise swamp everything. The Irvine, Michigan Brookhaven detector went into a salt mine near Cleveland, Ohio, and began operating in 1982. Kamiokande went into a zinc mine in the Japanese Alps in 1983, and the last letters of its name stand for Nucleon Decay Experiment. That is what it was for. That was the entire justification. Neither of them saw a proton decay. What they saw instead, on the 23rd of February 1987, was a burst of neutrinos arriving from a supernova in the Large Magellanic Cloud, 160,000 light-years away. Kamiokande recorded 11 events. The Ohio detector recorded 8. 19 particles, inside about 13 seconds, and they were the first neutrinos ever detected from beyond the solar system. Masatoshi Koshiba shared the Nobel Prize for it in 2002. 2 instruments built to witness the death of the proton failed at their assigned task and founded the field of neutrino astronomy by accident. The search continued, and it scaled up. Let me take you inside the machine that now carries it. Go a kilometer down into the rock of Mount Ikano in Japan, along a mine tunnel, and you arrive at a cylindrical cavern 40 meters across and 40 meters tall. It is filled with 50,000 tons of water, purified continuously and so aggressively that it is corrosive. Water this clean will pull minerals out of anything you put into it, and it is filtered around the clock because a trace of natural radioactivity would drown the signal entirely. Light travels 60 or 70 meters through it before dimming appreciably. Lining the inner walls are about 11,000 photomultiplier tubes, each one a glass bulb half a meter across, each one capable of registering a single photon. They face inward, into the dark, and they do not blink. Somewhere in that volume are approximately 10 to the 33 protons. Every one of them is under continuous observation. If a single proton anywhere in that tank decays, the fragments will travel faster than light does through water, and a cone of pale blue light will spread out from the event and land on the wall of glass eyes, and the pattern will be recorded, and physics will change. It has been watching since 1996. Kamiokande was watching from 1983. Nothing has happened. The published limit from the flagship channel, a proton decaying to a positron and a neutral pion, is now that the lifetime must exceed 2.4 times 10 to the 34th years, at 90% confidence, drawn from 450 kiloton years of exposure between April 1996 and May 2018. 0 candidate events. Later searches in other channels have pushed past 400 kiloton years of additional exposure and continue to find nothing. 2.4 times 10 to the 34th years is roughly a million times the current age of the universe. The minimal version of grand unification predicted a lifetime at least 1,000 times shorter than that. It is dead. It was killed twice, in fact. The proton decay limits ruled it out, and independently, precision measurements at CERN's electron-positron collider found a value for the weak mixing angle that the theory could not accommodate. I want to be careful here, because this is where the story is usually told badly. Grand unification as an idea is not dead. Larger symmetry groups and versions incorporating supersymmetry survive, and they generically predict proton lifetimes in the range of 10 to the 34th to 10 to the 36th years, just past the current limits. Some favor a different decay channel entirely, one producing a kaon and a neutrino, which is harder to see and less tightly constrained. The program has room. What it does not have is a result. A larger detector is being built in the same mountain. Hyper Kamiokande will hold several times the volume of its predecessor. Construction and commissioning are expected to be finished by the end of 2027, with data taking from 2028, and it should extend the reach by roughly another order of magnitude. But stop and consider what has actually happened here, because I think it is one of the more remarkable things human beings have ever done, and it is almost never described as such. People dug a cavern under a mountain. They filled it with the purest water on earth. They lined it with 11,000 glass eyes and turned off the lights and sat in the dark and waited, for 4 decades, for one single proton out of a number of protons that has no name, to fall apart. A thing that has never been observed to happen anywhere, ever, in the history of observation. It did not happen, and that nothing, that carefully measured, patiently accumulated, 40-year-long nothing, is one of the most informative results in modern physics. Every year of silence excludes another slice of theory. The absence has done more to shape what physicists believe than almost any positive discovery of the same period. That is what the good version of this looks like when it does not work. And all of it, every word of the last three parts, concerns three forces. We have not yet dealt with the fourth. Notice the phrase, grand unification. Not total unification, not unification of everything, grand, which sounds comprehensive and is not. In its standard technical usage, grand unification means unifying the strong, weak, and electromagnetic forces. Gravity is not in the sentence. It was left out deliberately, and it has been left out for 50 years, because nobody knows how to put it in. The obstacle is not a shortage of effort or ideas. It is specific, technical, and thoroughly understood, and understanding it is the difference between thinking of quantum gravity as a hard problem and recognizing it as a different kind of problem. Quantum field theory produces infinities. When you calculate anything beyond the crudest approximation, you find contributions from processes at arbitrarily high energy, and the sums diverge. This was regarded as a catastrophe in the 1930s and was solved in the 1940s by a procedure called renormalization. The idea is that the divergent quantities are not observable in isolation. What you actually measure is the combination of a bare parameter and its infinite correction. So you absorb the infinities into a small number of measured quantities, fix those against experiment, and everything else becomes predictable. In quantum electrodynamics, there are only a handful of parameters that need absorbing. Once they are fixed, the theory predicts everything else, and it does so with a precision that remains the most accurate agreement between theory and experiment ever achieved. The electron's magnetic moment matches calculation to roughly 12 significant figures. Now try it with gravity. There is a detail about Newton's constant that turns out to decide everything. The three quantum couplings are dimensionless numbers, pure ratios, with no units attached. Newton's constant is not. In the natural units physicists use, it carries dimensions of inverse mass, squared. That single fact means that as you go to higher and higher energies, each additional layer of the calculation requires a new kind of correction term that was not there before. The number of parameters you must absorb is not small, it is infinite. A theory that requires infinitely many measured inputs predicts nothing at all. You can always match any result by adjusting the next parameter, which means the theory can never be wrong, which means it has stopped being physics. This was suspected for decades and settled in 1986, when Mark Goroff and Augusto Sagnotti completed a calculation showing that pure quantum gravity diverges at the second layer of approximation in a way that cannot be absorbed. The demonstration was definitive. Quantum general relativity, treated the way we treat every other force, does not work. It works fine at low energy. As an approximation valid for weak fields and modest energies, quantized gravity is perfectly serviceable, and it gives sensible answers. The problem arrives as you climb, and there is a specific place where it stops giving answers at all. Let me take you there. Begin with something at human scale. A grain of dust on the bedside table. Shrink by a factor of 10,000, and you are at the size of an atom, a fuzzy sphere of electron cloud. Shrink by another factor of 100,000, and the nucleus resolves, a dense knot at the center of a great deal of empty space. Shrink again by 1,000, and you are inside a proton, in the churning gluon field where almost all of your mass turns out to live. Keep going. Past the quarks, which have no measured size at all. Past the scale, where the Large Hadron Collider's beams can resolve structure. Past every distance that has a name or an instrument. 20 more orders of magnitude down, you reach 1.6 times 10 to the minus 35 meters. The Planck length. At that scale, the energy required to probe is so enormous and gravity's response to energy so unavoidable that the act of looking creates enough concentrated energy to collapse the region into a black hole, and the picture does not blur. It does not go out of focus the way a microscope image does at its limit. The equations stop returning numbers. Distance, as a concept, stops doing the work we ask of it. The corresponding energy is 1.22 times 10 to the 19th gigaelectronvolts. The Large Hadron Collider reaches about 10 to the 4th. We are 15 orders of magnitude short of the place where the theory breaks, and that place is where the answer would be. There is a related silence worth naming. Every other force has had its carrier produced and measured, the photon, the W and Z, the gluons. The graviton has never been detected, and there is a serious argument that it never will be. Freeman Dyson pointed out that a detector sensitive enough to register a single graviton would have to be so massive that it would collapse under its own gravity before completing the measurement. Some recent proposals dispute the details, but nothing resembling an experiment exists. And it is worth being clear that gravitational waves are not the same thing. Detectors have measured those directly since the 14th of September, 2015, and it was a magnificent achievement. But a gravitational wave is a classical ripple in the field, not a single quantum of it. Measuring radio waves in the 1880s was not the same as detecting a photon. We have heard the field, we have never seen its particle, and we may never. Now the second problem, which may be deeper than the first. The Higgs boson, discovered in 2012, has a mass of about 125 gigaelectronvolts, perfectly ordinary as particle masses go, except that quantum mechanics says it should not be. Every particle the Higgs couples to contributes a correction to its mass. Those corrections are not small adjustments. They are proportional to the highest energy scale in the theory. If the theory holds all the way up to the Planck scale, then the corrections are around 10 to the 19th gigaelectronvolts, and the observed value is 125. 17 orders of magnitude too small. It is not impossible for that to happen. Positive and negative contributions can cancel, but to leave 125 behind, they have to cancel to something like 32 decimal places. Nothing in the standard model requires that cancellation, arranges it, or protects it. It simply has to be true, by arithmetic accident, to a precision no other coincidence in nature approaches. That is the hierarchy problem, and here is what makes it the same problem we have been circling all night. Ask why the Planck scale is so far above everything else, and you are asking why gravity is so absurdly weak. The two questions are the same question in different clothing. The 17 orders of magnitude in the Higgs mass and the 36 orders of magnitude in the strength ratio are two views of one gap. Which brings back the paperclip, that little magnet on the bedside table, lifting a piece of steel against an entire planet, is the everyday face of the deepest quantitative puzzle in particle physics. It looks like a party trick. It is a demonstration that two of the four fundamental forces differ in strength by a factor for which nobody has an explanation, and that the mass of the particle responsible for the whole electroweak structure sits, without protection, 32 decimal places away from where quantum mechanics would put it. The proposed answers were serious, and they were testable. Supersymmetry pairs every particle with a partner whose contribution cancels the dangerous corrections exactly, making the cancellation automatic instead of accidental. Composite Higgs models make the Higgs a bound state rather than a fundamental particle, so there is nothing to correct. Large extra dimensions propose that gravity is not weak at all, that it is a normal strength force which leaks into dimensions we cannot enter, and appears diluted to us because we only see a slice of it. Every one of those answers predicted new physics at or near the energies the Large Hadron Collider can reach. That was not incidental. If the new physics is much heavier, the cancellation it is supposed to explain has to be fine-tuned all over again, and the solution stops solving anything. The Large Hadron Collider has been running since 2010. No superpartners, no composite structure in the Higgs, no extra-dimensional signatures, no deviation from standard model predictions anywhere that has survived more data. Short-range tests of gravity itself have now confirmed the inverse square law down to about 50 micrometers with no departure, closing off much of the extra-dimensional territory from a completely different direction. The answers were beautiful, and they made predictions, and the predictions did not come true. There is one more structural oddity about gravity that deserves stating on its own, because it explains the strangest fact in this entire subject. Gravity has only one sign. Electric charge is positive or negative, and cancels. Color charge comes in three kinds and confines. The weak force cannot leave a nucleus, but mass energy comes in one variety only. There is no negative mass, no gravitational shielding, no way to build a room where gravity does not reach. Every additional gram adds, and nothing subtracts. So the weakest force by a factor of a million is the one that assembles planets, ignites stars, shapes galaxies, and determines the structure of the universe at every scale above the molecular. It does not win because it is powerful. It wins because it is the only one that never stops. That is where physics stands with the fourth force. It is the one we feel, the one we understood first, the one whose strength we measure worst, the one that cannot be quantized, the one whose weakness has no explanation, and the one left out of the phrase grand unification on purpose. So what is left? What do physicists actually propose now in the face of all this? There are answers. There are 4 of them, roughly, and they are not equally comfortable. The first answer is that all 4 forces are vibrations of the same object. String theory proposes that the fundamental constituents are not points, but extended objects, and that the different particles we observe, electron, photon, gluon, quark, are different vibrational patterns of the same kind of thing, the way a single string on an instrument produces different notes. Its strongest argument is one it did not choose. When you work out what patterns are allowed, a massless spin-2 state appears in the list, unbidden. A massless spin-2 state appears in the list, unbidden. String theory was originally invented in the late 1960s as a model of the strong force, and the compulsory graviton was considered a defect, a wrong prediction that helped get the theory abandoned for that purpose. 6 years later, somebody suggested that a theory which cannot avoid producing gravity might be a theory of gravity. It remains the only framework in which a mathematically consistent quantum theory containing gravity has been written down. That is not nothing. It is, in fact, a great deal. The costs are severe. The theory requires 10 or 11 dimensions of spacetime, and the extra ones must be curled up small enough to hide. The number of consistent ways to do that curling is commonly quoted at around 10 to the 500th. Each one gives a different universe, with different particle content and different force strengths, and there is currently no principle that picks ours out. Consider what that means for our question. We wanted to know why the coupling constants have the values they do, rather than being free parameters. A framework with 10 to the 500th solutions has not obviously reduced the number of free parameters. It has relocated them. The second answer is to stop trying to unify anything. Loop quantum gravity takes the view that unification was never obligatory, that the pressing problem is quantizing gravity itself, and the other 3 forces can be left where they are. Instead of putting gravity into the language of particle physics, it quantizes space-time directly. The result is a picture in which geometry is granular. Area and volume come in discrete quanta, with a smallest possible area on the order of the Planck length squared. There is no smooth continuum underneath. Space has a resolution. The program has produced genuine results, and it makes no attempt whatever to explain why there are four forces or why their strengths differ. Its practitioners would say that is a separate question, and possibly a question with no answer. The third answer is the most radical, and I find it the most interesting, because it dissolves the problem rather than solving it. What if gravity is not a fundamental force at all? In 1995, Ted Jacobson showed something startling. Einstein's field equations can be derived from thermodynamic assumptions about horizons and heat flow, not approximated, derived as an equation of state of the same logical type as the relationship between the pressure, volume, and temperature of a gas. In 2011, Eric Verlinde argued that gravity is an entropic effect, arising from the way information is distributed, rather than from any fundamental interaction. If that line is right, then the failure to quantize gravity is not a failure. It is the correct behavior. Nobody tries to quantize temperature. Temperature is not fundamental. It is what an enormous number of underlying degrees of freedom look like when you stop tracking them individually, and asking for a quantum of temperature is a category error. On this reading, there are not four forces. There are three, plus a statistical consequence of the way information is arranged. And it would explain the pattern we have spent all night collecting. Why is one of the four different in strength by 38 orders of magnitude, different in having a single sign, different in its mathematical structure, and different in refusing to quantize? Because it is not the same kind of thing as the others. It never was. That is an explanation rather than a description. It is also unproven, and it has real difficulties reproducing everything general relativity gets right. Before the fourth answer, there is the matter of what happened to the third of the great hopes, because its collapse is the reason this part exists at all. Supersymmetry, as we saw, arrived with three gifts. It made the coupling lines meet, it protected the Higgs mass from runaway corrections, and it handed over a dark matter candidate for free. For 30 years, it was the overwhelming favorite. Textbooks were written on the assumption that the Large Hadron Collider would find its particles within a few years of switching on. It has not been ruled out. Superpartners could simply be heavier than expected. But heavier superpartners reintroduce precisely the fine-tuning that supersymmetry existed to abolish. If the cancellation only works when you adjust the masses by hand, you have replaced one unexplained coincidence with another. The most elegant answer physics had is now in the position of being possibly true and no longer useful, and nothing has arrived to replace it. That, more than any single failed experiment, is the strategic situation in particle physics today. There is one hint from the string side worth mentioning, because it is the sharpest one anybody has. In 1997, Juan Maldacena proposed a correspondence in which a theory of gravity in a curved space-time is exactly equivalent to a gauge theory without gravity living on its boundary. The same physics, written twice, in two languages that look nothing alike. If that is telling us something general, then gravity and the gauge forces may not be two things that need joining. They may be one thing already, described from two sides. The fourth answer is that there is no answer. This is the landscape position, and it goes like this. If the underlying theory permits an enormous number of stable configurations, and if the universe realizes many of them in regions far beyond anything we can see, then the coupling constants are not fundamental at all. They are environmental. They are like the distance from the Earth to the Sun, a quantity no theory derives, which has the value it has in our neighborhood, because a great many neighborhoods exist, and we could only have appeared in one where the number permits appearing. The uncomfortable support for this comes from how sensitive our existence looks. The production of carbon in stars runs through a resonance whose position depends on the strong force strength at roughly the 0.5% level. Shift it, and the carbon does not form. Adjust the relative strengths of the strong and electromagnetic forces modestly in the other direction, and hydrogen becomes unstable. The four numbers we cannot explain are also four numbers that, if they were much different, would have produced a universe with nobody in it to ask about them. I want to sit with this one for a moment, because it is the answer that costs something. Everything we have followed tonight has been built on an assumption so basic that it usually goes unstated, that when you find an unexplained number in physics, there is a reason for it, and the reason can be found. That assumption has been vindicated over and over for 4 centuries. Kepler's orbits had a reason. The spectral lines of hydrogen had a reason. The periodic table had a reason. The landscape position says, not this time. There is no derivation. The strength of gravity is not the answer to a question. It is a local fact, like the weather, and asking why gravity is 10 to the 36 times weaker than electromagnetism is like asking why this particular Tuesday was overcast. That may be the truth. It may also be the most convenient possible way to stop looking, and that is precisely the objection to it. A framework that explains any observation equally well has told you nothing about which observation to expect. It is very difficult to be wrong about the landscape, and being able to be wrong is what makes an idea useful. So those are the 4 positions, and none of them can currently be distinguished from the others by any experiment anyone knows how to perform. Which leaves one strategy, and it is the one most working physicists are actually pursuing. If you cannot reach the energy where the answer lives, look for tiny deviations at the energies you can reach, small cracks, at ordinary scales that a much heavier structure might leave behind. That is why the muon's magnetic moment has absorbed decades of effort. The muon is a heavier cousin of the electron, and its magnetic properties can be both measured and calculated to extraordinary precision, so any disagreement between the two would point to something not in the standard model. Fermilab's final result, announced on the 3rd of June 2025, achieved a precision of 127 parts per billion, better than its own design goal. Whether it disagrees with theory turns out to depend on which theoretical prediction you use, because 2 independent methods of calculating the hardest part of the prediction currently disagree with each other. The crack, for now, may be in the calculation rather than in the world. That is where the most precise confrontation between 3 of the 4 forces and reality currently sits, unresolved and possibly a matter of arithmetic. It is a strange place for a field to be. Not idle, the work is careful, enormous and honest. Stuck is the better word. And so we arrive back at the question we started with, which I have deliberately not answered. So let me answer it plainly, the way I promised at the start. Why do the 4 fundamental forces remain physics' greatest mystery? Not because we know nothing about them. We know an enormous amount. We know their strengths to varying precision, their ranges, their carriers, their symmetries, the way each one changes as you climb in energy, and the exact mathematical form of every interaction any of them can have. The standard model is the most accurately tested description of nature ever constructed. This is not ignorance. It is a mystery for 4 specific reasons, and they stack. The first is that 3 of the 4 are the same idea and will not merge. Electromagnetism, the weak force, and the strong force are all outputs of a single construction, demand a symmetry locally rather than globally, and the force falls out as the price. Change the ingredient, get a different force. 3 instances of one machine. Their coupling strengths, extrapolated upward, converge toward a single value at an energy 12 orders of magnitude beyond any instrument we could build. Everything about them says they are pieces of one thing, and the merger has never been demonstrated because the one clean consequence of it, that a proton must eventually die, has been watched for by 50,000 tons of instrumented water under a Japanese mountain for 4 decades, and the answer has been nothing. Not a hint, not a candidate, 0. The second is that the fourth force is not built from that idea at all, and breaks the mathematics on contact. Gravity comes from the geometry of space-time. Its coupling has the wrong dimensions, which means that quantizing it the way we quantize everything else requires infinitely many measured inputs, which means it predicts nothing. That is not a technical inconvenience awaiting a clever fix. It has been understood in precise detail since 1986 and repaired by nobody. The third is the numbers. 38 orders of magnitude of range between the strongest force and the weakest, with no derivation, no pattern, and no theory that produces a single one of those values. They were measured and inserted by hand, and the same gap, seen from the other side, is the hierarchy problem. The Higgs mass, sitting 17 orders of magnitude below where quantum corrections should have dragged it, surviving only through a cancellation to something like 32 decimal places that nothing in the theory arranges or protects. The fourth is that every beautiful answer to the first 3 predicted something we could look for, and we looked, and it was not there. Supersymmetry predicted partner particles at reachable energies. Grand unification predicted proton decay. Large extra dimensions predicted departures from the inverse square law at short distance. Composite Higgs models predicted structure in the particle we found. All of it testable, all of it tested, none of it confirmed. Which brings back a phrase from earlier tonight, and I want to give it its second meaning now. The lines almost meet. I introduced that as a technical description of 3 coupling constants converging and missing, but it is also, at this point, a fair description of the entire enterprise. Every road in fundamental physics arrives close to the same place and stops just short. The couplings nearly unify. The proton nearly decays, just past the reach of the current detector. The muon's magnetic moment nearly disagrees with theory, except that the theory currently disagrees with itself. Supersymmetry nearly works, if the particles are a little heavier than we can see. String theory nearly predicts our universe, out of 10 to the 500th candidates. Almost everywhere, for 50 years. And the number 4, which I said at the beginning, is not a natural number for a universe to choose, may be the largest almost of all. If the convergence means what it looks like it means, then 4 was never a fact about physics. There was one force, at a temperature no experiment will reach, and the universe cooled, and it shattered, and we are standing in the cold end of that process, counting the fragments and calling the count fundamental. We do not know if that is true. That is the honest position, and it is worth saying clearly because there is a version of science writing that never quite admits it. Nobody knows why there are 4 fundamental forces. Nobody knows why they are these 4. Nobody knows why the strongest is a million times the weakest. Nobody knows whether that ratio is a deep fact awaiting explanation or an accident of the region of the universe we happen to occupy. There are 4 coherent positions, and no experiment currently distinguishes between them, and at least one of them is built in a way that makes distinguishing impossible in principle. That is not a failure. That is a field arriving, after 4 centuries of extraordinary work, at a precise description of the shape of what it does not know, which is a genuine achievement, and a rarer one than it sounds. Most of human history has consisted of not knowing things without being able to say what they were. It is also worth saying that this is not a story that has ended. It is a story that is currently waiting. Under that same mountain in Japan, a larger cavern is being finished. Hyperkamiokande is expected to be commissioned by the end of 2027, and to begin watching in 2028, with several times the volume of the detector that has been silent for 30 years, and roughly an order of magnitude more reach. Somewhere in the next decade, in the dark, under a kilometer of rock, one of two things will happen. Either a cone of pale blue light will spread from a point in that water and land on a wall of glass eyes, and a proton that had lasted since the first second of the universe will be gone, and the four will have been proven to be one. Or it will not, and another slice of theory will quietly close, and the almost will get a little wider. Nobody watching that tank will know in advance which evening it will be. That is the part I keep returning to. The most consequential experiment in fundamental physics consists, in practice, of a great deal of very clean water and a great many people being patient for a very long time. There is no drama in it at all. There is just the accumulation of nothing, carefully measured, year after year, by people who understand exactly how much a well-measured nothing is worth. And there is something in that I find quietly comforting, rather than frustrating. We live inside a set of rules we did not choose and cannot yet explain, and those rules have been generous. The strong force is strong enough to build carbon, and not so strong that hydrogen is unstable. The weak force is reluctant enough that the sun burns for 10,000 million years instead of exploding. Electromagnetism is exactly what it needs to be for chemistry to be rich rather than trivial. And gravity, 36 orders of magnitude beneath its nearest neighbor, is so faint that it took an entire planet to hold you gently in a bed tonight, and no more firmly than that. 4 numbers. Nobody knows where they came from. All 4 of them had to be almost exactly what they are, for there to be anybody wondering about it. Thank you for spending these hours with me, walking slowly through the 4 forces and the long, patient, unfinished attempt to show that they are one. If you found this worth your evening, a like or subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time you pick something up off the floor, that the effort you feel is the weakest thing in the universe, and physics still cannot tell you why. Good night, and may you never look at those 4 numbers the same way again.